Thank you. So thanks. First, of course, I need to thank the organizers for putting together this nice conference, nice location. Even the weather is cooperating. It's not too hot, right? So thanks for inviting me. Oh, and let me just say it's Ohio State University. It's not Ohio University. That's a big no-no. You can't do that in Ohio because there's another university in Ohio. It's Ohio University, and that's a sin to commit. Okay, so it's the Ohio State. Okay, maybe I do need the analog, the classical. What's happening here? Okay, let's see. Now it's not working. Now it froze. Of course, it was okay when I was testing it out. What happened? Now it's working? Okay. Well. Okay. Oh, okay, great, thank you. All right, so all right. So we're going to tell you about our, so we're a quantum transport group, so we do transport studies of 2D materials. So today I'm going to tell you, this is basically the three topics I'm going to tell you today. I'll work on superconductors, insulators, and semiconductors in 2D materials. Okay. All right, so first let me explain what is flatland. This comes from this book by Albert Iwan, which published in the 1860s or so, where there's a flatland, the romance of many dimensions, where they talk about, this is Square, which is a hero, lives in the flatland, which means a two-dimensional being. He visits point land, zero-dimensional, one line land, one-dimensional, and a space line, which is three-dimensional. With three dimensions, so it's opening up its perspective to many dimensions. Okay, so of course today there should probably be instead of square, we're going to have hexagons, and instead of so it's going to be two-dimensional instead of, so for example, one-dimensional buckyballs and zero-dimensional buckyballs, one-dimensional nanotubes, and three-dimensional graphite. Okay, so flatland, of course, refers to two-dimensional materials. But of course, there's another meaning of flatland, and this is because, this is a map of the US, and we're located somewhere here in the middle of Ohio State. And this area is like really, really extremely flat. It was under the glacier. So this is really extremely flat. You can see it's really, the variations is less than 200 meters. And locally, we actually have all the street names. I think we really want to have some mountains. So we have things like Summitville, Ridgeville, cliffs. But if you look at the map, it's really about 10, 20 meters, 10, 20 meters in altitude. So it's okay. So anyway, so it's very flat. Okay, so all right, that's where. Okay, so how about flat bands? So you already heard a lot about flat bands, and so when a flat band is just really referring to this energy, this band structure dispersion. And so when you have, when this is very flat, which means the velocity, which is proportional to the slope, is small. And so when you have small velocity, which means the kinetic energy is small, the potential energy is large, and so that the interactions dominate. So for example, you can look at this alpha, which is ratio between the Coulomb energy and the Fermi energy. And so it's roughly given, okay, what's happening? Okay, roughly given by this. Okay, so but why is interactions important? And this is what I like to show. We say we're physicists, we love interactions. may or may not be the human kind, but definitely, the electronic kind. Because with interactions, this will give us the this interesting correlator states like superconductivity, magnetism, insulator, charge density waves, and various correlator insulators. Okay, so here this is a brief outline of talk. I'm going to first tell you about superconductors, how quantum geometry enables superconductivity in the flat band. I'll tell you about recent work. This is IMPRESS, that we have seen dominate correlated insulating state and fractional fillings in twisted bilayer graphene by a large angle, not a magic angle, but a relatively large angle. And finally, I'm going to switch gear a little bit. So the first two are on twisted bilayer graphene, and the last topic, if I have time, is I'm going to tell you about the work of observation of octets in pentagonal 2D semiconductors. Okay, so, all right, so first topic, so this is led by my graduate student Haidong Tian, using Zhang and Xueshi Gao. And so this joint project with Mark Barkras at OSU. And so theoretical guidance and support is given by my colleague Mohit Randaria and Fan Zhang at UT Dallas. And of course, Taniguchi group provided provided the HBM crystals like for thousands of other groups in this field. Okay, so again, we talk about flat band. Now, what if we just push this to the limit, right? What if we truly have flat band, meaning the dispersion is completely flat, it's like horizontal line, and then which means that the velocity of the charges are 0. Now you can think, how can we going to have a conductor? How does the electricity conduct, let alone a superconductor? Okay, so this is so a little bit more quantitatively how about in a superconductor. So now we have flat band, the velocity is 0, the effective mass goes to infinity, and so if you plug in those numbers for the equations for the BCS theory of superconductivity, for example, superconducting gap is proportional to the Fermi velocity, and if you use Picard's argument for coherence length, that's proportional to Fermi velocity, and the superfluid stiffness, which is this parameter which governs the electromagnetic response of superconductor. Really, it's like essence of a superconductor, right? It tells you how robust the superconductor is. It's inversely proportional to the effective mass. So I think this is already, Dr. Zhou Wang yesterday already tell you about this, talk about the kinetic inductance, which is related to superfluid stiffness. So the question is, if you plug all this number in, they're all going to be 0. So this apparently produces a paradox. How can you going to have a superconductor if all these important parameters are 0? Okay, so in the past, people probably cop out by saying, oh, well, maybe it's not really flat. It's not flat enough for us to care, okay, which is probably true in a lot of other superconductors. But now, of course, with this emergence of the flat band, imaginary angle twisted bilayer graphene, and the superconductivity inside, then things actually change. Okay, so this you probably know about this. Ooh, yeah, this one keep happening. Okay, so we know that this work, seminal work from MIT group, where they have seen the correlated insulating state. For example, at integer fillings, when you have integer number of electrons per superlighter cell, and the superconductivity when you are a little bit away from the integers, like you can think it's like you're maybe doping the integers, although I'm not sure that's the correct way to think about it. But okay, so we'll see superconductivity, for example, on the either side of this insulator state at when you have 2 electrons per unit cell. Okay. Okay, so now this is so what we set out to do. We have so we have a really nice device. This is angle is, oh, I think maybe this is out of order. Oh yeah, I should put this. Okay, so this device is angle is 1.08 degrees. And here we're showing just the resistance as a function of backgate voltage And the top axis labels the filling factor, the number of number of holes per unit cell. Okay, so we have, so there's a peak at the charge neutrality point. And then we have peaks at, when you have 2, 3, and 4 holes per unit cell. And so the one at 4, this filling factor 4 refers to, this is the band insulator, where the one at filling factor 2 and 3, this is the correlated insulating state. And superconductivity is observed when we have about roughly between 2 and 2.5 holes per unit superlattice cell. Okay, so and this is a device of very low resistance in the normal state, so which actually we can estimate just the coherence length, which is about basically the channel length, so that we're in the really the ballistic, the mean free path is about channel length, so we're in the ballistic regime. And another thing is that I want to draw your attention is that we have these peaks at filling factor 2 and 3. And these are associated with so-called reset of the Dirac spectrum, or so-called Dirac revival story. And so this is work done by other groups, a number of other groups, which means you have these 4 mini Dirac cones from the spin and valley flavor, and every time you fill one, so you fill, and then you reset, so you fill the lower half of one and you reset to fill the other. Okay, so basically you go through this reset of filling of this mini Dirac cones, and this also has been verified by the RXY, the RXY, which means the density measurements. Okay, so this, basically what happens is that every time you charge, for example, the Fermi level moves through the when we have this when we fill 2 holes per unit cell, then the effective charge density resets to 0. Okay, so now we're going to measure everything. It's going to be measure relative to this half filling state. Again, this is not what our work. This has been so this so-called Fermi, this Dirac reset story has been verified by a number of other measurements. For example, the capacitance and the inverse compatibility measurement. Okay. I don't need to go back. No. Okay, this. Okay. Well, what's happening? Okay. All right. So let me go. So this slides. Okay. So first, just characterize the superconducting state. So this is actually again everything looks. This is just consistent with all other reports of superconductivity, except I just have a really nice sample. So for example, here you were looking at the resistance as a function of charge density, which is the horizontal axis, and so the upper graph plots the density, temperature, and the lower graph plots the magnetic field. And the dark blue area is the superconducting region. So we can see that now this disappears. Wow, I think this is a little too advanced for me. Let me try to. Maybe I do need the analog one. Oh, okay.
Very successful.
Yeah.
Okay, sorry.
Thank you.
Yeah, you have to open it up 1 second. Okay, perfect. And then you can put the orange. We give extra time to Jenny.
Wow, okay. Thank you for the theorists coming to rescue. I'm sure you don't want to become an experimentalist. And, oh, wait a minute. What's happening here? Okay. All right. So, so this is superconducting dome. Okay, so this is what we call TC dome. This is a BC dome. All right. So then we're going following the conventional Kupras. We're going to call the highest TC point. This is the optimal filling. To the left is what we call overdoped regime, and to the right we call underdoped region. Okay, and so the TC, this is basically the we define it as 20% of the normal state resistance, and so that's 2.2 Kelvin at the highest doping. But if you take the practice these days is to take 50% of normal state resistance, And so in that case, will be about 3.1 Kelvin. And that puts it up to this will be the highest amount of highest superconductivity in twisted bilayer graphene reported. And the coherence length is basically related to the upper critical field. For example, basically, again, we define this as 20% of normal state resistance. And that's given by, so it's about between 60 to 150 nanometers. Okay, so again, this is just, all these are just all agrees with previous report. It's just a really nice sample with relatively higher TC. Okay. Okay. Oh, wow, this is really out of order. Okay. All right, so those are, okay, so now we're going to do something a little bit unusual, which has not been done so much, which is the nonlinear transform, meaning we apply a bias voltage. So here this graph plots differential resistance DVDI as a function of current density and charge density. Again, charge density we measure from the so-called half filling point, meaning from when we have 2 electrons per unit cell is 0. Again, because of this Dirac revival story. And we actually, now we actually apply a small magnetic field, 0.2 Tesla, to suppress superconductivity. So this is in the normal state. So what's interesting is that we have seen this, okay, well, it looks like a mouse, and with lipsticks, okay? And so that's, so this actually looks pretty weird. So what's happening here is that we have, so this kind of lipstick, okay, correspond to really the peaks in the differential resistance. Okay, so for example, this one, these are the peaks. And so what happens is that we have, when a small bias, there is a low but finite resistance. Okay, so again, this is a normal state, so low but finite resistance, and then the resistance increases sharply to reach a peak before it disappears, and then this peak kind of almost goes away linearly from this half filling point. Okay, so and you will raise the temperature to this oh, sorry, what happened? Okay, I raise the temperature, so this is the 5 Kelvin data, then the peaks disappears. Okay, so this is actually pretty strange. But what's even more strange is that we suppress the superconductivity. We reduce the magnetic field to 0, so superconductivity appears. And this is really the superconducting region. It's a really dark blue area that's 0 resistance. Okay, but most of this actually, looks actually about the same as in the normal state. So we're just going to set that to half transparency and lay it on top, so you can see really this area looks about the same, right? And then and then except then you'll have this region. Okay, so I'm going to plot this I'm going to call this a critical current where the peaks are. So in the normal state and the superconducting state, I'm going to plot the same graph. Now we can see it looks like this. Okay, so this is the normal state, the red, and this critical current in the superconducting state, which is following this structure here. Okay, so now this is actually really strange. What's strange is that why do we have critical current like DVDI peaks in the normal state? And then, so the first question. Second question is why are the critical currents the same in the superconducting and the normal state? And this is in the underdoped region. And in the overdoped region, they actually bifurcate, right? So they becomes different. Okay, so this actually you had us scratching our head for a little while, and so it turns out. So the normal state behavior, so this work from the Manchester group came out. It turns out they actually have some similar thing in the normal state. So what they have is they have a graphene HBM superlattice, twisted bilayer graphene, but not at matching angles, so either a little bit bigger, a little bit smaller, and also monolayer graphene with constrictions. But what they have seen here is DVDI, for example, this blue curve here, have really looked very, exactly the same as what we have observed. Okay, so this one you have to rotate it 90 degrees, but then you'll see the similar behavior. But what they see is, one difference is that the current density they observe, this critical current density is a lot higher, right? So it's about 100 times larger than what we have seen. We have seen the basic 100 so we have seen it's a few hundred nanometer per micron, okay? Okay, so what they have explained, this is actually a really nice explanation, is that the so-called Swinger mechanism of electron hole pair production. So let me walk you through this. Okay, so all right, so for example, we start with this is a direct cone, and we have a little bit of charge in there. So this is like a martini in a martini glass. Okay, so wine in a martini glass. Okay, so it's like this, and this will have zero bias. This will be something like this. Now we start applying a bias. This will have a little bias, and which means we're going to, it's like this martini glass in an accelerating car, and the sum of charges is going to try to climb, we're going to climb up this right-hand wall, okay? And now you can try to accelerate the car some more, so meaning we apply more bias, and so eventually, all the charges is going to be something like this. All the charges will climb up the right-hand wall. And so remember that the current density is given by charge density times electron charge times velocity, right? And the velocity will be the average, will be the weighted average of all the charges. Okay, so if you have parabolic dispersion, you can always get higher velocity. You just climb up the wall some more because the slope will be changing. Okay, so there will be, well, so you can climb up some more. You can also drive more current through. But for direct distribution, once all charges go up to this wall, and that's it, right? The velocity is constant. So all the charges will have the same velocity, and theoretically, at least classically, that's all the current you can carry in this case. So therefore reach a peak in the dVdI. But if you now insist driving some more current through, okay, so then so now this Swinger mechanism comes into play, which means the holes will start to conduct at a large electric field. And so this is basically, and this actually have also been seen features in RXY, okay? Okay, so really nice thing is that this peak where it happens corresponds to really the characteristic band velocity of this Dirac band. Okay, so this will give us a really easy, a nice way to measure Fermi velocity. Or let me just say characteristic band velocity. Okay, so and now it also makes perfect sense that this critical current happens at much larger. It has much larger value for their twisted bilayer graphene. That's because the samples are now at magic angle, so the Fermi velocity is larger. It's a lot higher. And our sample is at magic angle, and so we have a very small Fermi velocity. So we are at the flat band. Okay, so really this tells us, give us a way to measure Fermi velocity. So now we can just measure Fermi velocity. This is again in the normal state. We have Fermi velocity of roughly 1,000 meters per second. So that's order of 3 orders of magnitude reduced from monolayer graphene. Yes?
Sorry, just a conceptual question on the previous slide about measuring the Fermi velocity. This argument really only applies in the ballistic limit, because the current limitation, if you say that the current is independent of the impurity density, right? Because the impurity, the scattering length is not appearing in this argument.
I believe it's actually, I think it's independent. I believe in the theory for this, well, this is of course a very simplified picture. I believe in the detailed calculation. I think this by Farco's group. They actually, I think they actually assume there is scattering involved.
But then there should be an unknown prefactor which relates your charge velocity to your critical current. If scattering is involved, right? Because if scattering is not involved, then I'm not quite understanding the picture, but maybe.
Well, okay, I think my understanding is that this actually does not depend on whether it's ballistic or diffusive. Okay, so I took out for the interest of time, I did not have this slide, but we actually also calibrated this technique versus for twisted bilayer graphene versus other techniques. for example, Schubert-Haas and quantum Hall and capacitance measurements. And I think it actually agrees, well, there's some scattering, but it actually roughly agrees, consistent. Yeah, okay, so let me continue. Okay, so this just tells us we can measure the Fermi velocity. Again, okay, so maybe it's not, maybe it's not exactly Fermi velocity, but I would say it would be a characteristic velocity of charge carriers. And this, again, it would be some sort of, we can imagine this is sort of weighted the average Fermi velocity, average velocity of charge carriers. And so that's about 1,000 meters per second, near half filling. So there's a little bit of change, but roughly on that order. So this tells us it's extremely slow. And now the fact that this peaks disappear below 5 Kelvin confirms really small Fermi energy. Okay, so this just tells us how flat the band the system is. Okay, so we're also going to just to answer the first question. Well, one of the questions we posed is that why do we have this kind of critical current and superconductor in the normal state and in the superconducting state? Why do we have they are the same in the underdoped region and they're different in the overdoped region? So in the underdoped region, we really understand that the supercurrent now is limited by the Fermi velocity. So basically the same mechanism that limits current in the normal state limits supercurrent in superconducting state. Okay, so this basically tells us we have a new limit to supercurrent in the flat band, in the direct flat band. In the overdoped region, then turns out basically this is a classical conventional limit to supercurrent, which is a depairing mechanism. This happens when basically the h bar kf times the velocity of the superfluid is smaller than the gap. Then this will have this is so-called depairing, and this is limits the supercurrent. And in this case, because the gap decreases, like the TC decreases, so the gap decreases, and therefore so in this case, it's limited by the depairing. Okay, we can take both into account by this very crude model, which saying that okay, whatever kills the superconductivity will kill it first. Okay, so it's basically you can either be killed by the this limiting Schwinger limiting mechanism, or be killed by the depairing mechanism. So the velocity is given by the smaller of the two mechanisms, and so this would be the this green dotted line, and so that sort of agrees actually pretty well with the experimental data. Okay, so now we can go try to look at the answers I posed at the beginning of this talk, which is, okay, so what if we now plug in the numbers for all the BCS theory of superconductivity? So now if we just plug in the numbers, we can see, because now we know Fermi velocity, we can estimate effective mass by just saying it's h bar VF divided by KF. And now this, okay, so now this number makes sense. So for example, the superconducting gap, the ratio between gap and TC, this will become 0.05. Of course, BCS will give us 1.7, and it's even higher for the for example, unconventional superconductors such as high TC. The Pipars argument will give us a coherence length of 2.6 nanometers, but what we observe is 55 nanometers at least. The superfluid stiffness, right, is given by this equation. So that gives us 10 to the 6 inverse Henry, but the superfluid stiffness is related to TC by this Nelson-Kosterlitz criteria. So if we plug in this number, this will give us a 10 millikelvin TC. Of course, we have measured experimentally is between 2 and 3 Kelvin. Okay, so this, of course, now this number makes sense. Okay. So that seems to have a paradox. Of course, the theorists come save the day. by the quantum geometry, which so Dr. Zhou Wang already talked about this yesterday. So again, I also want to give a lot of give credit to Professor Thomas' work, where they have studied superfluidity in topological non-trivial band. This is back in 2015. This is before the experimental discovery of twistor bilayer graphene. So okay, so what they come save the day is the quantum geometry. So again, this is my one slide understanding of quantum geometry. So you can define this gauge invariant quantum geometric tensor. The imaginary part is a Berry curvature, and the real part is so-called Fabini-Study quantum matrix, which measures the distance between two quantum states and of the overlap of linear wave functions. And so there's a really nice review article from Thoma and Bernovics in 2022, where they, so basically it's this overlap of this wave functions and the interference will enable superconductivity. So I think since this pioneering work, now again now because of flat band in the twistor bilayer graphene, there's actually a lot of theory work. Again, this is not a complete list, so a lot of theory work in this area. Okay, so now what we have, okay, so now the question is, can we quantify superfluid stiffness? Again, so we have, we can now measure superfluid stiffness with, with a traditional method, just because we have such a small material, small samples. So now we're going to just going to do some back envelope calculations. We use fundamental equation of superconductivity. For example, momentum is proportional to the gradient of the phase, and the current density is proportional to superfluid stiffness times the momentum, and the magnitude of the gradient of the phase is roughly the inverse of the coherence length. So we just combine this equation. Again, this is all just really fundamental equation of superconductivity. Then we obtain this equation here. So the nice thing about this equation is that the critical current and the effective and the coherence length are measured, experimentally measured, right? And then we just divide by flux quantum. So this is, again, this is not exact formula, but it is, I would say, probably good within a factor of 2 or maybe 50% or so. Right, but then what we try to explain is about order of magnitude, right? This one of the magnitude difference. So this should give us a good, somewhat good estimate of superfluid stiffness. Okay, so here's what we have obtained. We're plotting superfluid stiffness as a function of effective charge density. The dotted line is the black dotted line is the classical BCS equation. And we see it's real, and the red line is what we obtained from just using this equation. Again, using experimentally obtained critical current and the coherence length. So now you can see that not only, so they're all by order of magnitude, and also this, the classical equation has the wrong dependence in density. Okay, so what we conclude is that really this classical BCS contribution, determined by the kinetic energy, and so that accounts for about 10% of the superfluid stiffness that we measure experimentally, and and then the rest comes from the interaction. So we just do some really simple dimensional analysis. We say, okay, the superfluid stiffness related to the kind of the gap, and related E squared over H bar squared. And we put in Fudge factor should be order of unity B here. And so that's, this is a green dotted line. So that's, whoops. And so that accounts for the data, again, not perfect, but in the absence of a more complete theory, I think this is reasonable considering how crude this analysis is. So it's reasonable agreement with the data. So this tells us, again, there's just the superfluid stiffness is not set by the kinetic energy like in classical superconductors, but by the interactions. Yes? Yes.
One question, maybe it's a stupid one. Now, in the low doping regime, you have a larger, distance between what you are measuring and what the theory is providing you. While before that, when you were just starting the
Fermi velocity or the velocity of carriers, it was exactly the opposite. So the lower doping, it was better. It was following more the trend than here.
Yeah.
Is it correlated somehow?
Oh, that's a good question. Okay, we actually have not thought about that. Again, this is a very, very crude analysis. I think we are hoping for a better theory for this.
Because they
Yeah.
rely on the same measurements and same experiments.
Yes,
So
they are
the
related.
index,
Yeah.
So they could be just like a mechanism that velocity goes. We can discuss.
Yeah. No, I think that's a very good observation. Yeah, but I guess right now what we're trying to say here is sort of order of magnitude explanation. Yeah. But also, I think we do hope for better theory for both the critical current and the superfluid stiffness in the twisted bilayer. Okay, so let me just summarize this part. So twisted bilayer graphene can have extremely slow-moving charges, a flat band. So in theory, you can actually Fermi velocity can go to 0 if you hit exactly the magic angle. So there's a new current limiting mechanism, which is a swinging limiting mechanism in direct superconductors, and quantum geometry dominates the contribution. So, and the BCS equation will need to be revisited in this case. Okay, so now let me tell you about the work in the fractional fillings, the insulator state. Okay, so this work is led by my student Haidong Tian and Emilio Codicido, and again in collaboration with Mark Baccaras. The theory is done by Una King's group. So Dan Mao and Kevin Zhang are students in Una's group. Again, HBN crystals. Okay, so now, for example, if you look at literature, you're going to see this type of plots. So plots, for example, resistance, in this case is inverse compressibility, versus magnetic field, and this is to be charge density. And you see this kind of lots of lines like this, and then you're going to have some vertical lines, or some slope lines. And so this so-called, sometimes we call this one-year diagram. So what this is basically, so they all follow this equation here. So this traces the gap state in the magnetic field. So and this is n over n naught is n naught is basically the number of charges per superunit vector cell, and B is like the effective magnetic field. It's a magnetic field. It's number of flux quantums you can fit into the superunit cell. And so now this T, the slope, is basically a Chern number. So the vertical lines is Chern 0, and the slope lines will have certain Chern number, and the S will be the number of bound charges per unit cell, which corresponding to the basically to the intercepts in the horizontal axis. So often these T and S numbers are integers, but can be fractional. For example, you can fractional quantum Hall effect. Okay, so that'll be fractional T. But so far for twisted bilayer graphene at magic angle, integer fillings are dominant. So you're going to see most of the integer fillings, although fractions are seen, but they are usually pretty weak. For example, I think, for example, there's a fraction here. Right, there's some fraction here, and maybe this one, depending, I think, extrapolate to some fractional number here. Okay. So again, so this usually we see integer fillings. Okay, so now what we have seen, so those are magic angles. So now we actually have some large angle devices. And if you ask me why do we do large angle, that's just because we obtain large angle. I say, oh, what the heck, let's measure it. Okay, so but turns out we actually, we see interesting stuff. So this is an angle of 1.32 degrees. So this is microsiemens. This is conductance. That's a function of gate voltage, and the top axis plots again the filling factors. So now we have, okay, so at charge neutrality point we have 0. So this is a dip, okay, the peak in resistance, a dip in conductance. and then we have 4, and so these are the band insulators, 4 and -4. Now we can see, now we have very robust insulating states here. So at 8/3, plus minus 8/3, and plus minus 4/3. Okay, so these are these peaks. Okay, and on top of that we have features at basic 2/3. Okay, so there's 2/3. I think there's some features here. Okay, so 2/3 and 10/3. Okay, we do see some you know, this state at half filling, that a filling factor 2, which is this one, but they actually now that's robust. So we have a little bit at -2 here, so it's a little bit of feature here, but they're actually not as robust as the ones at 8/3 and 4/3. Okay, so these are actually really prominent insulating states at the 1/3 fraction fillings. Okay, so I think we're just doing this. Okay, so now we can look at the temperature dependence. So the 8/3 states is actually, it's like really pretty insulating, and you kind of you can feed this to a to thermal activation model. Oops. And this have a gap of about actually about 20 milli electron volt, and then the 8/3 state is actually non-monotonic dependence on temperature. We can also do the magnetic field dependence measurement. So this is in the perpendicular field, and so this is a one-year diagram, and we can see the 8/3 and 4/3. They are actually Chern zero, so they're vertical lines. They're Chern zero, so they don't have a Chern number. And then in the perpendicular magnetic field, where we see that so perpendicular field, parallel magnetic field is an in-plane field. Basically the further stabilize the 8/3 state, but the 4/3 state has non-monotonic dependence. So this suggests there is some sort of probably competing state in the 4/3. Okay, so all right, so and then we have another device. This is even large angle, close to 1.6 degrees. And so this one is again. So we have very similarly we see insulating states at 8/3 and 4/3. Okay, so actually, what's really interesting here is you can probably see some lines. Maybe it's not doesn't come quite nicely here, but you can see some features that's horizontal features, meaning they're independent of charge density. Okay, so it's like this, like this. Okay, and those are actually the sag bands. This happens when the flux quantum per unit cell is basically 1 over some integer, and so this. But from this sag band, we can. So these sag bands are periodic in 1 over b. So from that, we can actually back out the size of the unit cell in the sample. So it turns out that the size of unit cell is actually about 3 times the size of the unit cell from the twist angle. Okay, so basically we have a triple unit cell reconstruction. So from this data, which is actually so that's that's a nice observation. Okay, so this analog also have some issues. Okay, so that's which I think this is actually that's a nice observation, because I think triple unit cell reconstruction has been predicted by some theory, and it's people were saying, oh, maybe we can't see it in transport measurement. Maybe we have to do STM measurement. But so it turns out we can see it in transport. So to explain this, we engage the help of Woona Kim, who actually they had predicted the fractional correlating insulating state at 1/3 fillings. Well, what they did is actually in magic angle twisted bilayer graphene, but turns out these states are much more dominant in large angle devices. Okay, so there's a theory where it happens is that they look at this 1 year wave functions. 3 is basically they have a 3 clothes, and this produce saturate some geometric frustration, produce closely competing ground state. And so they can, the calculation is consistent with work. Okay, so, yeah, yes?
The competing ground state, and what's, is it like analog of CDW or?
Yeah, so basically it's in the A-third, so there's A-third is, yes, it's like CDW, but the 4/3 there is some competing with some, they have some spin valley flavors, which are competing. That's why they have non-monotonic dependence, actually in temperature and magnetic field. Yeah. Okay, so how much time do I have? Oh, okay. Okay, so should be probably enough time. Let me tell you this is our recent work in this 2D semiconductors. Okay, so this work is led by my student Yuxing Zhang. So the Roland Kawakami group performed the second harmonic generation measurements. Josh Goldberg's group provided the sample, the crystals, and the high magnetic field measurement was done in the lab in Florida in collaboration with Dmitry Smirnov, and Fan Zhang did the band structure DFT calculations. Okay, so this is, so we'll change gear a little bit. So this is a 2D semiconductor, and so this is palladium selenide. So it's actually kind of interestingly has a pentagon structure. It's pocket pentagon. So project on the planes like this, but the we know pentagon by itself is in the plane does not tile it does not tile a plane, right? But so it's a pocket, but the underlying lattice is actually rectangular lattice, very, very close to a square lattice. So A and B lattice constant is differs by 1% or so. Okay, so there is actually a number. So this is a layer material. Again, we can exfoliate. So there's a number of work in this area which they show this. So these are the claims. These are air stable. It is gapped. And high mobility, again, the high mobility here, what they call high mobility is up to about 200 centimeter square per volt second. And also it's usually done at very high bias and room temperature and high temperature. Okay, so but large area growth of field layers has been demonstrated. Okay, so there's some of the recent work. Okay, so what we try to do is we're going to try to improve the mobility by putting it on silicon. Well, we're going to compare the mobility of silicon oxide and also HBN, and then we're going to also try to improve the mobility and look at the contacts. So we actually we exfoliate a few layer devices on silicon oxide. We use chrome gold contact. Chrome gold actually gives reasonable contact. So we can actually, state 0, it's ambipolar. We have a mobility of between 10 to 20 and at room temperature. And then, but if we leave it outside, so remember this was actually claimed to be air stable, but we leave it outside, it turns out it's just, they will just shift. The curves we're going to shift, the mobility will decrease. By day 27, actually there's, really there's no gate response, and the resistance when it's highly doped becomes actually much worse. So it is not completely air stable. So we can anneal it. So nice thing is that we can anneal it. So this is after annealing. It does recover the electron mobility, but it becomes very strongly electron doped. I think it's probably a formation of selenium vacancies. And this, what happens that if you leave outside that in air, we believe what happens is probably partial oxidation with some outside. Okay, of course, you will put it between HBN, and we have graphene contact, and it's much nicer. So we have a very high mobility, and this is very stable. Okay. So we can do some characterization. This is done at, I think, room temperature. For example, we can have very large saturation current, greater than 340 milliamp per millimeter. And we believe we can achieve a much larger saturation current with some optimization. The field effect mobility is actually, so these are two devices. One is, I think, 3 layers. The other is 5 layers. So the 5 layers have higher mobility up here. So this, it's about between 150 to 750 at room temperature, and between 2,000 and 10,000 at low temperature. And this mobility is, kind of follows this power law dependence, so it's probably limited by phonons, and then saturating probably limited by impurities at low temperature. Okay, so now we can, with that kind of mobility, we can do quantum oscillation measurements. So this is, what's interesting is that the oscillations turns out to have 8-fold degeneracy, which was unexpected. So what turns out happens is we have 2-fold for spin, and there's 4-fold for valley, and this comes from the valley in the, this valley in this Boilon zone, so this from the square lattice, from the square lattice valleys. So, so we have 4-fold valleys, so I think that's kind of interesting. And we can measure the effective mass is about 0.3. Okay, and then so lastly, we can have break order degeneracy and really high field. This is like 29 Tesla. And we can break order degeneracy here. And we also have in-plane field measurements. So for interest of time, so this has been published. We have, what we can observe, we can conclude is that we first, this is cyclotron gap, and then the Zeeman gap is broken. And then lastly, the valley gap is broken. Okay, so why is that interesting? We thought it's okay. So it's a it's a nice 2D semiconductor, but probably maybe not in this case. I don't know how much quantum we have. Well, we have quantum Hall effect, but okay. But I think what we really want to do is we want to twist the square lattice. So far, all the work in twisting this twistronics are done on honeycomb lattices, honeycomb lattice. So like PMDs and graphene. So what we want to do is we want to twist a square lattice, and so there's a recent some theory work, for example, Ashman's group and from this Forquy group, where they have calculated the flap when you twist bilayer square lattice, what can happen. So in particular, this work from Ashman groups is only dependent on symmetry-dependent arguments, so it should be quite robust, independent of the details of band structure. Where they have predicted that the flat band flattening can occur in this case. And but what we want to do is say this is a square lattice. It's actually a simulator to realize a nice Hubbard model with scattered optical symmetries. And so there are some predictions, right? The theoretical predictions. It would be nice. We can, this will be our quantum simulator to simulate this model to see can we see any of this metal insulator transition and ferromagnetic ground state of superconductivity. So okay, so that's what we hope to do. Okay, so lastly, let me just thank my colleagues and thank and collaborators. And okay, thank you for coming listening.